In this video, we're going to simplify certain rational expressions that have square roots in them. Some people think it's impolite to have a square root show up in a denominator. I'm not so worried about that, but sometimes when a square root is in a denominator, there's always a way to rewrite it as having the square root in the numerator instead. So we'll talk about a way to do that. On the other hand, if we do have a square root in the numerator, there's a way to rewrite it so the square root is in the denominator instead. And you'll see examples in your future calculus class on why you'd want to do that. For now, we'll just use it as a tool of simplification. Now, before we get started, all of this is based on the idea of the difference of squares. Now, the difference of squares is a basic idea of factoring or simplification, depending on how you think about it. Basically, if you've got a squared minus b squared, that can be rewritten as a minus b times a plus b. That's the factorization of that difference of squares. Now, what we're going to do is we're going to recognize in our expressions either an a minus b or an a plus b, and we're going to multiply it by the other. And what that'll do is that'll allow us to square both a and b. Now, why would we want to do that? It's because either a or b is a square root. So by squaring both a and b, we can get rid of those square roots. But of course, if we're talking about a fraction and we've got square roots in the denominator, I can't just multiply the denominator by something. If I do that, I have to pay a price. I have to multiply the numerator by the same thing. Now, if you've got a minus b, then a plus b is the radical conjugate. Or if you've got a plus b, a minus b is its radical conjugate. They're radical conjugates of each other. That's kind of the lingo we'll be using here for these examples. So if I take a look at the first example here, and I take a look at the denominator, it's where the square root is. Now, the radical conjugate of that denominator is 4 minus root 3. So I'm going to multiply top and bottom of this expression by 4 minus root 3. Now again, you may be wondering why on earth we would do this. Just wait for it. All I want you to realize at this moment is that we are allowed to do it. So I'm multiplying top and bottom by the same thing. I'm always allowed to do that. I haven't fundamentally changed my fraction. Now in the top, well, I guess we get 20 minus 5 root 3. Not very exciting stuff. But in the denominator, we have this difference of squares idea here. Okay? I have a 4 plus root 3 times a 4 minus root 3. That perfectly fits that structure right there. So we can rewrite it as 4 squared minus root 3 squared. And that allows us to get rid of the square root. So we've got 16 minus 3. So that denominator simplifies to simply 13. Sometimes this method is called rationalizing the denominator because we've taken what started off as an irrational denominator, root 3 is an irrational number, and now our final answer has a rational denominator. In fact, it's an integer. Okay? Let's try another example, this time with some variables in it. Let's take a look at the next page. Why don't we do this number 4 here? So let's say I look at that denominator there. I could multiply top and bottom here by the radical conjugate of that denominator, which would be 5 minus root x plus 1. And of course, if I do it to the denominator, I have to do it to the numerator as well. Okay. So in the numerator, well, I guess I could expand it out. We'd have to FOIL it. Okay. When I do that, I'm going to get 8 times 5 is 40. 8 times negative root x plus 1. Simplest way I can write that is negative 8 root x plus 1. Negative root x plus 1 times 5. Again, the simplest way I can write it is like that. And negative root x plus 1 times negative root x plus 1, that's plus root x plus 1 squared. Well, that's kind of nice. But better yet, in the denominator, here we see we have a difference of squares. So I can rewrite this as 5 squared minus root x plus 1 squared. Now in the numerator, if we start simplifying, we've got 40 minus 13 root x plus 1. Those are like terms. And then root x plus 1 squared is x plus 1. In the denominator, we've got 25 minus x plus 1. Okay? And I can simplify both the numerator and denominator just a little bit more. We've got like terms. I've got 41 minus 13 root x plus 1 plus x. And in the denominator, we've got 25 minus x minus 1, or 24 minus x. Okay? So there's my rationalized denominator. Notice the only square roots that show up are in the numerator, whereas in the original expression, we had square roots in the top and in the bottom. Now please try out examples number 3 and 2 for yourself here and practice this idea, and take a look at a few web work questions to try out as well. Thank you.